Welcome back to The Deep Dive. Today we're diving into the machine, specifically how routers think, how they build the map that moves all of your data.
It's a huge topic.
It is. Our mission is, well, simple but critical. We're taking a deep plunge into the core logic of IPv4 routing, really dissecting how a router decides where to send every single packet it touches.
And we're talking about IP routing. It's the fundamental process that ensures a packet gets from, say, your laptop to a server across the world, potentially crossing dozens of networks.
And the health of that entire journey, really the entire internet, hinges on one thing:
the router's internal map, its routing table.
So when you look inside that map, how does a router even get its information? There are really only three ways it learns about the world.
The first one, which is sort of the mandatory starting point, is connected routes. These are just the subnets that are physically attached to the router's own interfaces. The router learns these automatically.
Okay, so what it can see directly. Then you have the ones that engineers put in by hand.
Right, the deliberate instructions, static routes. You enter these directly with the uproute command.
And finally, there's the really complex one, the automated one.
Dynamic routes. That's where routers talk to each other, they exchange information using protocols like OSPF or EIGRP. We'll definitely save that for a future deep dive.
For sure. But today, we're focused on the bedrock. The routes the router figures out on its own connected, and the ones we tell it static. Understanding these is, it's the crucial context for every single packet decision. Okay, let's unpack this journey. And we start, maybe surprisingly, not with the router, but with the host. Your PC, your server, the device that first creates the IP packet.
Exactly. Before that packet even leaves the network card, the host has to make a really critical layer 3 decision.
It has to ask a simple question, right?
A very simple question. Is the destination local? It checks the destination IP against its own IP and subnet mask.
To see if it can reach it without needing a router.
Precisely. If the destination is local, on the same LAN segment, the host knows it can deliver it directly. It'll just use ARP, the address resolution protocol, to find the other guy's MS address and build the frame right there.
But if it's remote, anywhere else in the world,
then it knows it needs a guide. It has to send that IP packet to its default gateway,
which is its first hop router.
Yep. And the crucial detail is how it builds that frame. The destination MSE address in the frame isn't the final destination's MC. It's the MSE address of the default gateway.
Okay, so the frame arrives at the router. Now, the router has a job, and I understand it's a very specific 5-step process.
It is highly standardized. The first 2 steps are just about prep work and quality control.
So what's step 1?
Step 1 is the receive frame check. The router asks, should I even bother with this? It has to pass the FCS, the frame check sequence, to make sure the data isn't corrupted.
And the address has to be for the router itself.
Right. The destination MS address has to match one of its own interfaces. If either of those checks fail, the frame is just dropped. Gone.
Assuming it passes, then what?
Step 2 is de-encapsulation. The router strips off the layer 2 header and trailer like the Ethernet frame to get to the IP packet inside. All that layer 2 info that got the packet to this router, it's irrelevant now.
And now we get to the core of it. Step 3.
This is where the brainpower comes in. Step 3 is the routing decision. The router takes that IP packet and compares the destination IP address against every single entry in its routing table.
Looking for the best match.
The best match, usually the longest, most specific one. That match tells it which interface to send the packet out of.
And once it knows where it's going, it has to get it ready for the next leg of the journey.
Which brings us to step 4. Encapsulation. The router takes that original unchanged IP packet and wraps it in a brand new data link frame.
One that's appropriate for the outgoing interface.
Yes. So if it's going on another Ethernet port, it might have to do a whole new ARP lookup to find the MASCII address of the next router in line.
And then the final step is pretty obvious.
Step 5. Transmit. It just sends that newly built frame out the door.
The key takeaway here, and this is what trips a lot of people up, is that the data link frame is destroyed and rebuilt at every single router hop.
Absolutely. The IP packet inside stays the same, like a letter. But the envelope, the frame, is constantly being opened, thrown away, and replaced with a new one for the next post office in the chain.
Okay, that sets the mechanics perfectly. Let's circle back to populating that routing table, that map. Routers start with what they know automatically.
The connected routes. In the routing table, you'll see them with a code C. They represent the entire subnet that the router is physically plugged into.
So the moment I configure an IP on an interface and it comes up,
the router automatically calculates the subnet ID or the prefix and bang, it installs that C route into the table, as long as that interface is up.
But when I run a show beep route, I don't just see a C route. Right under it, there's always an L route. Why two routes for the same interface? Seems redundant.
That is a brilliant question, and the answer is all about efficiency. The C route, the connected route, defines the whole neighborhood like 192.168.1.024.
Okay, the whole block.
The local route, the L route, is much more specific. It's a route for the router's own IP address on that interface, and it uses a 32 prefix length.
Ah, so the C is the whole street and the L is the router's exact house number.
Perfect analogy. It's purely for efficiency. If a packet comes in that's destined for the router itself, like a ping or an SSH session, that 32 route is the most specific match possible. It wins immediately, and the router knows this is for me, instead of wasting cycles thinking about forwarding it somewhere else.
That makes a ton of sense. It shortcuts the decision process.
It does. And a little troubleshooting nugget for you.
Yeah.
So we've all been there trying to configure an interface. The router's iOS is smart. It will reject the EPA address command if you try to use the subnet ID itself or the broadcast address.
The first or last net address in the subnet.
Exactly.
Okay.
It also stops you from putting two active interfaces on the same router in the same subnet. That would create a logical nightmare, so it just says no.
All right, now we get to the routes that need a human touch. Static routes, code S. You still see these everywhere, even in huge networks.
Oh, yeah. They're vital. Great for simple setups, for specific traffic policies, or as we'll see, for backup paths.
So you use the iproute command, you give it the destination network and mask, but then you have a choice.
You have to tell it how to get there. Your two main options are specifying the outgoing interface, like Gigabyte Ethernet 1000 or
the next hop IP address, the IP of the router next door.
Right. And this is a big deal for new engineers. While both can work, one of them is dramatically preferred, especially on Ethernet.
And that's using the next hop IP. Why is that so much cleaner?
It comes down to clean network logic. If you just point the static route out an interface on an Ethernet link, you're basically forcing the router to pretend that remote network is directly connected.
Which it isn't.
Which it is not. And that unnatural situation forces the network to rely on a mechanism called proxy ARP.
Proxy ARP. That just sounds like something I want to avoid.
You do. It forces the neighboring router to effectively lie on your behalf. Your router ARPs for an IP on the remote network, and the neighbor intercepts it and replies with its own AMC address, pretending to be the destination.
That's messy.
It's very messy. It breaks the clean separation of layer 2 and 3. But if you just use the next hop IP address, your router's logic is simple. To get there, my next step is router B. It's clean, predictable, and doesn't require any proxy shenanigans.
That's a fantastic insight. Okay, so what if a packet comes in and it doesn't match any of these specific connected or static routes? We need a catch-all.
And that is the static default route. You might know it as the gateway of last resort.
The famous quad zero route.
The one and only.
Yeah.
0.0.0.0.0.0.0.0, or just 0.0.0.0.0. This route is designed to match everything that doesn't have a more specific home. In the routing table, you'll see it marked with an S star, S.
That asterisk means it's the candidate default.
Yep, and it's perfect for, say, a small branch office. It only has one way out. It doesn't need to know every route in the corporate network.
It just needs one instruction. For anything I don't know about, send it that way.
Precisely. And we can also go the other way, from super general to super specific, with static host routes.
This is a route for just one single IT address.
One single host. You configure it with a mask of 255.255.255.255, which is a 32 prefix length.
Why would you ever do that?
It's an override. Imagine you have a critical server, and you want its backup traffic to always use a special high-speed link, while everyone else uses the normal path. You can create a 32 host route just for that server's IP to force its traffic down that special path.
So we've populated the table with C, L, and S routes. But now the big question. A packet arrives, and its destination matches multiple routes. How does the router choose?
Right, this is where the sorting hat comes on. And there are two ironclad rules. The first, and most important, is specificity. We call it the longest prefix match.
The most detailed map entry wins.
Always. If a packet is going to 10.1.1.110, and the table has a route for the whole 24 network and a host route for 32.
The 32 wins.
Every single time. Specificity trumps everything else.
But what if you have a tie? Two routes to the exact same 24 network, but they were learned from different sources. Maybe one is static and one came from OSPF.
That's where the second rule comes in. Administrative distance, or AD. Think of AD as a trustworthiness score for the source of the information.
And lower is better.
Lower is better. The router trusts the source with the lowest AD. It's a tiebreaker.
What are the defaults we should know?
Connected routes are perfect, so their AD is 0-way. Static routes are very trusted. Their AD is 1. And dynamic protocols are further down the list. OSPF, for example, has a default AD of 110.
Okay, so that hierarchy of trust lets engineers do some really clever things, like floating static routes. Why would I ever configure a route but intentionally make it less trustworthy?
You do it to build a safety net. Let's say your main link from a branch office is a fast fiber connection running OSPF, which has that AD of 110. But you also have a slower, cheaper backup VPN link. If you configured a normal static route for the backup, its AD of 1 would always win, and you'd never use your fast fiber.
Right, the backup would become the primary.
Exactly. So what you do is configure that backup static route with an intentionally high AD, let's say 130.
Higher than OSPF's 110.
Right. So now, as long as the main fiber link is up and the OSPF route is in the table, the router ignores your AD 130 static route. It's floating in the configuration unused.
But if the fiber link goes down,
OSPF pulls its route from the table. Suddenly, your floating static route with an AD of 130 is the best path available. It pops into the routing table, and traffic fails over to the backup link. It's a fantastic mechanism for high availability.
before we wrap, let's do a quick troubleshooting checklist, a classic headache. You type in a static route, it looks perfect, but it never shows up in the routing table.
Ah, yes, the disappearing route. First, the simplest check is syntax. Did the router even accept the command? If you accidentally use a host IP instead of the subnet ID, for example, the router just rejects the command.
So always check your history to see if it took it. Let's check number 2.
Check the interface status. If your static route points to an outgoing interface,
Like Gigabyte Ethernet 1000.
right, that interface must be in an up state. If it's down, the router considers the route invalid and won't install it.
And the third one, which I think catches most people when they use the next hop IP method.
This is the big one. It's a logical chain reaction. For a router to install a static route that points to a next hop IP, it must already have a valid route to reach that next hop IP.
So it has to know how to get to the next step before it can create a path that uses that next step.
You got it. If the path to your next hop router goes down, any static routes that rely on it will also disappear from the table. The router won't send traffic into a black hole.
Speaking of black holes, there's a really risky keyword you can add to a static route to just force it in no matter what.
There is the permanent keyword. If you add permanent to your iproute command, it tells the router to ignore all those sanity checks.
So the route stays in the table even if the interface is down.
Even if the interface is down, even if the next hop is unreachable. It solves the not appearing problem, but it creates a much worse one. You're now actively routing packets into a void. It's a tool to be used with extreme caution.
That was an incredible look into the absolute foundations of IP routing. We hit the essential 5-step packet forwarding process, that constant D and re-encapsulation.
Yeah.
We covered the automatic routes connected with a C, local with an L, and then the strategic power of all the S-type static routes, network, default, and even those super specific host routes.
And at the end of the day, it all boils down to a step-by-step logical process. It's governed by 2 simple rules. First, find the most detailed map entry with longest prefix match.
And if there's a tie?
Trust the most reliable map maker based on administrative distance. That's the whole game.
And as we sign off, here's a final thought for you to mull over. Considering the risks of using that permanent keyword to bypass safety checks and the hidden complexities of things like proxy ARP, how does knowing these manual nitty-gritty details influence your trust in the big, automated, dynamic routing protocols? Should an engineer ever fully trust the automated system, or does manual scrutiny and a solid backup plan always have to be the final check?
Knowing the fundamentals is always your best defense. Until next time.
See you in the next deep dive.